We will now specialize the equation of motion for Newtonian fluids of constant density. This is also known as Navier-Stokes equation. Now, let's just briefly remind ourselves of what the equation of motion is about. The basic idea in equation of motion was that the volumetric change of momentum in time within a volume element is a net momentum flux through the boundaries of the element plus any action of external body forces. And this net momentum flux through the boundaries as well as the action of the external body forces is precisely what we were doing during the shell balance. So if I put together that net momentum, we would basically get that the change of rho v for x momentum, the change of rho vx in time, so this is d dt, is equal to essentially what comes down to a divergence of my vector x momentum vector. So this is vector that looks at the x momentum transfer across x boundary, x momentum transfer across y boundary, and x momentum transfer across z boundary. And this is the action of the outside forces that can actually change the momentum. Now we have the equivalent idea for y and z directions. So basically I have three equations, one for each coordinate direction. Okay? Now when we pointed out in class, when we put that, we can actually figure out a shorthand notation that puts this into a vector form. So then I have d dt of rho v. V is basically vector vx, vy, vz, and I can think of this as a column vector, and my v is a column vector vx, vy, vz. And on the right-hand side, I have what I put together. So basically, if I take this, which is divergence of vx, as x coordinate of a vector, and I take this, which is divergence of phi vy, vector, divergence of a vector is a scalar, remember? So if I put that scalar as the second coordinate and this scalar as the third coordinate of a vector, then that vector I define as divergence of phi, where phi is tensor. And remember that tensor phi, our combined momentum tensor, had phi x, phi y, and phi z as column vectors. Okay? Great. So that's essentially what motivates definition of a divergence of a tensor. Divergence of some tensor phi, which can be written out here as this, is divergence of the first column, divergence of the second column, and divergence of the third column put together into a vector. So great. So now with that, this is just to basically make this this notation shorter. We actually had in class an exercise of what happens. So now I know that my phi has combined effects of pressure, shear stress, as well as convective momentum transfer. So now I want to know what is my divergence of phi with three different components. So it's basically, well, I go one by one. Divergence of P times identity matrix. We came up in class that is equal to gradient of P. So when I take divergence of this first element, I get gradient of P. Now I'm wondering, what is divergence of tau? When for that, I need to the definition of a fluid. If I take Newtonian fluid with constant density, then my constant density incompressible fluid dictates that divergence of V is 0. So when this is the expression for my shear stress in terms of for Newtonian fluids, then I'm really left with this. And I want to compute this. What is it? Well, I claimed in class that when I take divergence of tau, I should basically get this. So let's now get that. I will actually now elaborate on that. Okay. So first things first, I will basically define what is my gradient of V. this is gradient of a vector. So by definition, it's a full matrix that we also refer to as Jacobian. So it's dvx, dx, dy, and dvx, dz. So in my first row, I have all of the partial derivatives of vx. And the similar thing I have happening in the second row, just all of the partial derivatives of vy. And then a similar thing happening in the z row or third row. So this is Jacobian. So this is all of the partial, the combinations of all of the partial derivatives that I could have in a three-dimensional Cartesian system with respect to all of the coordinates of this vector v, vx, vy, vz. Now, what is now? So I said that if I want to define divergence of this, I would go column by column. So in this first row, I would have divergence of the first column. Or maybe I should call that x column. Right? And then divergence of the second column. And divergence of the third column. So what is this divergence of the first column? This is my first column. Okay? So this is a vector. This first column is a vector. And the way I normally take divergence, you will remember that I will take x derivative of the x coordinate plus y derivative of the y coordinate plus z derivative of the z coordinate. So divergence of a vector is this scalar. So let's take the x coordinate of the first coordinate, that's in this vector dvx dx, plus y derivative of the second, so dvy dx in this case, plus z derivative of okay, great. Let me actually look at this a little. So this is second order, basically double derivative vx with respect to x. Then we have d dy, d dx of vy, and d dz of d dx of dvz. We will now remember that this, I can basically see that this x derivative with respect to x is repeated, and I know that all of these, if I have nicely continuous and continuously differentiable function, I can actually flip the order in which I do derivatives. So this is equal to, well, there's nothing to flip in the first case, but basically d dx of dvy dx, dy, plus d dx of dvz dz. Okay? Again, because I can flip the order of differentiation for continuously differentiable functions. Awesome. So now I will recognize that here I have d dx of dvx dx plus dvy dy plus dv dz, which is equal to divergence of v, and that has to be equal to 0. So this first element is actually equal to 0. Now if I repeat things for the second column, and I have picked blue color, oh well, then I will have, again by the same analysis, d dx of dvx dy plus d dy of dvy dy plus d dz of dvz dy. And if I again flip the order of differentiation, I will get that this is actually ddy of divergence of v, and that is equal to 0 as well. And similarly, you can see where this is going. Similarly, when I take this third column, okay, I will get that this is actually equal by d dz of divergence of v after flipping order of differentiation, and that is equal to 0 as well. So essentially, divergence of a gradient of v is a 0 vector. So this part actually disappears. So now I'm wondering, okay, the second part, what is that equal to? So remember that is minus mu plus gradient of v transpose. When I wanted to take divergence as well, I will get minus mu divergence of v plus divergence of gradient of v transpose. We have just found out that this here is a 0 vector. This is remember that divergence of a tensor is a vector. Now I'm wondering what is DVD, divergence of the Jacobian transposed. Okay. Now Jacobian transposed is, I will just basically transpose the matrix that I had on the previous page for the Jacobian. So basically, what was my first column will become first row. So in the first row, I will have partial derivative with respect to x of vx, dy, and vz. And then I will have in the second row, so I will have partial derivative with respect to, so what was my second column will become second row. So now in the second row, I will have partial derivative with respect to y of vx, dy, and vz. And the similar thing happening in the third row, just now with respect to z. So now I want to take divergence of that. Again, I will proceed as before. So I will first take the first column, and I will take divergence of that first column, and that is basically what is in my first here is first column. And that is equal to b dx of dvx dx plus ddy of what? The second element plus ddz of the third. So I can see that this is equal to d square vx dx square plus d square vy dy square plus d square vz dz square. Whoa. And this, by definition, is Laplacian of V. No, I had Vx everywhere. Vx, Vx, Vx. This is Laplacian. Apologies for this omission. So this, by definition, let me properly erase. Okay. So this is Laplacian of Vx. Similarly, I will now change colors and take second column. So divergence of the second column, and you can immediately see how easy it is to make a little mistake. As I was talking and writing, I cannot talk and write in parallel correctly. So I made a small mistake, and then that propagated. So this is all x, and this is x. So now divergence of the second column is d dx of the first element, dvy dx, plus d dy of the second element, which is dy dy, plus d dz of the third, and that is dy vy dz. And this is basically second order derivative. Vx squared plus d squared vy dy squared plus d squared vy dz squared. And that is Laplacian of Vy by definition. Remember that Laplacian of any function, scalar function S, is second order. Okay, so you just go x, y, z. Excellent. And finally, you can see where this is going. The third column. I'm gonna do, let's just go with this. Why not? Okay. So this is going to end up being even without deriving it. So this is third column. And I invite you to do this calculation yourself. So what did we get? Okay. We got that this here indeed is Laplacian of V, where this by definition is Laplacian of V. This is just shorthand notation. And definition of Laplacian of a vector. Note that this is Laplacian of a scalar function. And that is it for now. So basically we got that divergence of tau is equal to minus divergence of transpose of the transpose, and this was a zero vector, and this was Laplacian, so minus Laplacian of V. Okay, so now remember that what we had is that d rho d rho v is equal to minus divergence of my general vector c plus rho g. And we have just, so this was p delta plus tau plus rho v plus rho g. This is a vector function. And I have just found out, so this is equal to divergence of p times identity matrix is minus gradient of P. We have proved that just a moment ago. Divergence of tau, and this is not a vector tau. Again, me talking and writing power. This is a tensor. So this is also a tensor. Divergence of tau is minus gradient of P plus mu plus V minus divergence of rho VB and plus rho G. I will transfer this part to the left-hand side, and then we have d dt of rho V plus rho VB is equal to minus V plus rho G. This really is Navier-Stokes equation. This portion, I will not go and prove it, is often also referred to as rho times material derivative of vector, and that's, you will find references to it in BSL. Material derivative. It's actually derivative in the coordinate system that is moving with the fluid. We will not go into details of it, but this part is what is expanded in your equation of motion. So if you compare to this is essentially what is expanded on the left-hand side of the equations in Appendix B6, and this is what is expanded on the right-hand side of the equations in Appendix B6. So this is Navier-Stokes equation. That is all. Let me know if you have any questions.